So, I'm kind of surprised nobody has brought this up yet or asked about it, but has anybody noticed something that was missing? We've done adding, subtracting, multiplying matrices. Nobody noticed that we haven't divided by matrices? You didn't even think about it?
So wait, time out. So when we're doing dividing with what is it, fractions, you just do the reciprocal. So are we finding the inverse of a matrix and multiplying that with the, okay, that's lame.
Okay, there is no division of matrices. Okay, but in a way there kind of is with this idea of the inverse. And what you were describing, Joe, is accurate. Instead of taking 6 and dividing it by 3, wouldn't that be the same thing as timesing it by 1/3? Okay, so matrix division in a way I guess could be described using an inverse. Okay, let's start with the inverse. First, we got to talk about what's called the identity matrix. In mathematics, there are certain numbers that are called identities, like the additive identity. You guys can come up with this. The additive identity is a number that doesn't change the value of another number when added to it. So what would it be? 0. 0 is the additive identity. There's a multiplicative identity, because if you take this number and multiply it by any other number, it doesn't change that other number. So what's the multiplicative identity? 1, right? The identity matrix is similar to a multiplicative identity. It's a matrix that when you take this matrix and multiply it by any other matrix, you end up with the same matrix you started with. So for a 2 by 2, the identity matrix is 1, 0, 0, 1. If you take this matrix and multiply it with another 2 by 2 matrix, you're going to end up with the matrix you started with. It's called the identity matrix. For example, if we had 1, 2, 3, 4, and I asked you to multiply that with the identity matrix, let's go through the process real quick. This first entry right here in row 1, column 1, you're going to take row 1 here and column 1 right there. You're going to go across the row down the column. 1 times 1 is 1. You add that to the next product, which is 3 times what? Which is 0. Okay, now let's move down to the next. This is row 2, column 1. No, we're not finding the inverse. I'm just showing you that this really is an identity matrix, because we're supposed to end up with, what are we supposed to end up with here as an answer? 1, 3, 2, 4. That's what we're supposed to end up with, if this really is the identity matrix. So how do we find this product here? 2 times 1 is 2. We add that to what? Where does the 0 come from? We go across the row down the column, so we have a 4 times 0, which is 0. Move over to the next entry here. This is row 1, but column 2. So row 1, column 2. What is that entry going to be? 0 plus 3. And then we go down to row 2, column 2. That entry is going to be 0 plus 4. So we do, in fact, end up with the same matrix that we started with. This is called the identity matrix. For short, it's given this symbol I, capital I with a subscript of 2. That means it's the identity matrix for a 2 by 2. For a 3 by 3,
1, 0, 1, 0, 1, 0, 1.
it's close. 1 0 0. What is it? Keep going.
0, 1, 0.
0 1 0.
0, 0, 1.
0 0 1. That's the identity matrix if you're dealing with a 3 by 3. And then for 4 by 4 and 5 by 5, you get the pattern, right? What would a 4 by 4 be? What would I? 1 0 0 0. 0 1 0 0. 0 0 1 0 0 0. Sounds like we're talking in binary. Yeah. It's similar to reducible echelon form. Yep. So, what's the big deal about an identity matrix? Okay, listen carefully. Write this down. Matter of fact, if a matrix, let's revise that. If a square matrix is multiplied by its inverse, the result is the identity matrix. So far we have not discussed on how to find the inverse yet, and that's not the point of this first objective. That's the second objective. And that's something that you should be familiar with multiplication, for example. If I took 3 and multiplied it with its reciprocal 1/3, what's the result of that? 1. And what's significant about 1? It's the multiplicative identity. Okay? Now if I take a matrix A and multiplied it with its inverse, now this is the notation for inverse. It's a capital letter with an exponent of -1. This means inverse. What should the result of this be? A matrix multiplied with its inverse should result in the I matrix, the identity. Okay? If the matrix is square. Yeah? A square matrix has the same number of rows as columns. So let's do example 1. Oh, matter of fact, you have to show both of these, by the way. Because matrix multiplication is not commutative, you have to show both cases of the multiplication equal the identity. Not just A times A inverse, but also A inverse times A. So example 1, show that the two matrices are inverses. So here's a matrix. First column is 2, 5. Second column is 1, 3. Next column is 3, -5. And -1. 2. We need to verify that these two matrices are inverses. How do we do that? Which order do we have to multiply them in? We have to do both. This one times this one and this one times that one. You have to show that both directions of the multiplication give you the identity matrix. So this is a two-part problem. So for part A, let's do the first one, 2, 5, 1, 3, times the second one. I'm sure that's not as interesting as what we're doing here. Am I right? So what is the matrix multiplication? Don't just wait for me to do it for you. What is it we're hoping for? to happen here? What is it we need to happen or should happen? We should get 1, 0, 0, 1. If not, then either we've made a mistake or these really are not inverses. So the first one is 6 minus 5. The next entry down here is 15 minus 15. Row 1, column 2 is negative 2 plus 2. Row 2, column 2 is negative 5 plus 6. So we do get 1, 0, 0, 1. But we've only verified the multiplication in one direction. The first one times the second one. We do have to verify it going the other way. 3, negative 5, negative 1, 2. Does the second one work?
Yeah.
This one's going to be 6 minus 5. This entry down here is negative 5 plus 5. This entry here is 3 minus 3. And this entry here is negative 5 plus 6. So we get 1, 0, 0, 1. What have we shown? That they are inverses, because both of the directions of multiplication produce the identity matrix. Okay?
Are there going to be some that are inverse with one leg but not the other?
Probably. And if that's the case, then they really are not inverses of each other. So, yeah, these ones are inverses. Nope. If you've shown that both multiplications produce the identity matrix, then that's sufficient. They are inverses. Do you notice anything? If we call this one A and we call this one A inverse, do you see any kind of relationship? Or let's go ahead, Jake.
A and B are switched, and then B and C are negative.
Is that what you're going to say, Addie? You guys see that? What happened to A and D here? They switched, and then B and C? That's something to keep in mind. Let's talk about how to find the inverse.
But how do we know
Of
which one is the inverse of the original?
No, that's a good question. Considering that this was matrix A, then that would be the inverse. Or if you consider this to be matrix A, the same pattern would have held. Now, let's keep it general here. We're going to have A, B, C, and D. Let's consider this to be matrix A. If matrix A is the general matrix, and this is only true for a 2 by 2, the process for finding a 3 by 3 is similar,
But so much harder.
but so much harder
Yay.
and more time consuming, which is, I know exactly what you wanted to hear. Then A inverse. It's a little bit more than the pattern that Jake and Addie mentioned. It's part of that. A and D have to switch spots, so this first entry becomes D, and then this down in the right bottom corner becomes A.
Would it be negative B and negative C?
Well, it becomes the opposite of B here and the opposite of C there, but there's a little multiplier out in front. We have to have a scalar multiplier, and that scalar is 1 over the determinant of A.
That's a hard equation.
This is the formula for finding the inverse. This will not be given to you on the exam. Okay? So I'm a little worried for some of you that during lecture time or doodling and sleeping and not doing much, and then when I come around to check off your homework, you haven't done it, or I just see answers written down, meaning all you did is copy answers. This next test is not, it's not that it's difficult. The material really isn't that hard, but it's very computation intensive. And if you don't know the exact right order due to the computations, if you're not careful with your minuses and you're subtracting negatives and that sort of thing, you're going to end up missing a ton of points. And if there's only 12 or 13 questions on the test, missing a few points here and there, is that going to be a big deal? Yeah, a big deal. And there aren't any test retakes in here. Okay, some of you I don't think really understand the gravity of not doing your homework and just dinking around during lecture time and not paying attention. Okay? But you're all adults. If you choose to do that, please don't come whining to me that your grade is not what you think it ought to be, because you've made the choice to be an idiot during class time and not do your homework. Anyway, let's see if this formula would have worked on that last example we had. Let's consider A to be, what was it, 2, 5, 1, 3. So if A equals 2, 5, and then 1, 3, then A inverse would be 1 over the determinant of A and we have to switch the spot of D and A, so this first entry becomes a 3, and then down in the bottom right corner we get a 2. And then B and C have to switch signs, so that becomes -1 and -5. All that's left to do now is find the determinant of A.
I got you with 1.
So the determinant of A is 6 minus 5, which is 1. So then 1 divided by 1 is, so A inverse is equal to 1 times 3, -1, -5, and 2. Isn't that what it should have been, though? 3, -5, -1, and 2. Let's do example 2. Try this one on your own. I'm going to give you a matrix. Find the inverse. So A is equal to 4, 2, 5, 3. Find the inverse. What happens with this 1/2? It multiplies into all the entries. So some of them don't divide in half, and that's okay. Just leave it as a fraction. So you're going to get 3 halves, then -1, then -5 halves, and then 2. And that's the process for finding the inverse of a 2 by 2. Okay? What's the point of all this? Let's move on to what's called matrix equations. and matrix algebra. Matrix equations and matrix algebra, they're related. One thing you got to keep straight, a matrix equation is different than an augmented matrix. A matrix equation comes from a system of equations, but it's not the same as an augmented matrix. So, let's see. Given the system of equations, 2x minus 5y equals 15. Second equation is 3x minus 6y equals 36. We already know how to form an augmented matrix, but a matrix equation looks like this. The first matrix is a matrix consisting only of the coefficients of the variables. So you're going to have a 2, 3 in the first column, and a negative 5, negative 6. It's actually where Cramer's rule came from. The next matrix is a column matrix. What that means is it's a matrix consisting of only one column. And those are your variables. Now, if it's called a matrix equation, the word equation implies we're going to have what symbol? Equal sign. So here's the equal sign. And then we have another column matrix. What do you think is going to go in that column? 15 and 36. Now this is just using symbols, okay? This coefficient matrix is given the symbol capital A. The coefficient matrix is given the symbol B, or x, lowercase x, and then this is given the symbol lowercase b. I don't know, just always given lowercase. I guess it really doesn't matter. So what we have there symbolically is ax is equal to b. Now, what is it in a system of equations that we're solving for? X and y, right? Now, in a matrix equation, this x column or this xy column is represented by this lowercase x. So in this equation here, what is it we're going to try to solve for?
X.
X. How would we solve for x? Knowing that we cannot divide by a matrix. We can't divide by matrix A like that because there is no division of matrices. You multiply by the inverse. What happens when you take matrix and multiply by its inverse? It cancels to the identity, but what is the identity? Essentially, what is the identity? It's just the number 1, essentially. Now, the order of multiplication is extremely important, you guys. Because you multiplied on the left side by A inverse, you have to multiply on the left side here. Matrix multiplication is not commutative. Do you see what happened here? We multiplied on the left by A inverse, so you have to multiply by the left. So how do we solve for our two variables using what's called matrix algebra? First, we have to find the inverse of matrix A, multiply it on both sides, and solve for our variables. This is called matrix algebra. You first set up a matrix equation, find the inverse. So let's try it here. First, find the inverse of A. So A inverse is equal to 1 over the determinant of A. Then we switch the spots of A and D, so this becomes a -6 on the top left and a +2 on the bottom right. Then B and C switch signs, so we're going to have a +5 and a -3. Now we have to know the determinant of A. What is the determinant of A? It's a pretty small number. it's negative 12 minus negative 15, which is 3. The determinant of A is equal to 3. So right, what we have now is 1/3 times negative 6, 5, negative 3, negative or positive 2. And I want you to stop here for a second. Normally, if you're just finding inverse and we're not doing matrix algebra, what would you do now? You take the 1/3 and multiply it into the matrix, right? If all I were asking you to do is find the inverse, that's what I would expect you to do. If you're using matrix algebra, it would actually be better if you leave this 1/3 out of the matrix for right now. Okay? You still could multiply it in there and finish the problem. It would make it a lot harder because you're going to end up with a couple of fractions in here, aren't you? So if you're using matrix algebra, leave this scalar out in front for the time being. Okay? Well, what do we do with A inverse? Because here's what we have now. We have the matrix equation, 2, 3, negative 5, negative 6, times the column matrix xy equals 15 and 36. What do we do with this inverse? Multiply on the left side here. And you have to keep the order the same. You cannot multiply it on the right side. You have to, I'm going to move this over, matter of fact. So this is going to be 1/3 times negative 6, negative 3, 5, 2, and then you multiply it by 15 and 36. Let's see, this is a 2 by 2 matrix here. And what is this one here? This is a 2 by 1. That's why it has to be in this order. If you tried to take this matrix and multiply it on the other side, you'd have a 2 by 1 multiplied by a 2 by 2. Would that be possible? No, that wouldn't be possible. Now what happens here with this matrix in red and this one in blue right here? It becomes the identity, which for our intent, I mean, it's essentially the number 1, which isn't going to change this xy. So what we have is xy is equal to whatever this product turns out to be. Okay. I would first multiply these two matrices together and then multiply by the 1/3. So this is going to be 1/3. Now what is the result of a 2 by 2 times a 2 by 1? A 2 by 1. So this is going to be 1/3 multiplied by another 2 by 1 matrix. So if I want to get the top entry in this 2 by 1 matrix, it's this row right here combined with this column right here. Row 1, column 1. The numbers are a little bit larger. What's negative 6 times 15? Yeah, negative 90. And we have to add that to 5 times 36, which is 180. Now I want you to just to stop for a second. Stop. Do you understand why I had you leave this 1/3 out? Because if we had multiplied by the 1/3, then you'd end up multiplying by fractions at some point in here, which is not going to be fun to do. Okay? So if you leave the 1/3 out of it and just multiply the numbers inside the matrix, and then at the very end multiply by the 1/3, it would have been the same. So what's this bottom entry here going to be? This is going to be row 2. So it's this row here combined with that column. So it's negative 45 plus 72. So xy is equal to 1/3 times 90, and then what's negative 45 and 72? 27. So then xy, now if we multiply the 1/3 in there, what do we get? 30 and 9. So your solution is the ordered pair 30 comma 9. That's called matrix algebra. Okay. Now you guys, this is not going to be something that you see me do. You say, oh yeah, I got it. You have to practice. You've got to practice. You've got to do the homework and not just go back and look at the answers and then write the answers down. Do the homework. Do the problem and then check your answer after you do it. Now let's just double check. 30 comma 9, does that really satisfy the system of equations? If we have 30 comma 9 as a potential solution, does that even work? 2 times 30 is 60. Minus 5 times 9, so that's minus 45. Does that work? Okay. 3 times 30 is 90. 6 times 9 is 54. 90 minus 54 is 36. So the answer really is 30 comma 9. If it didn't work out, you made a mistake somewhere, an arithmetic mistake. Now, think back to the last lesson when we were talking about determinants. Okay? Didn't you notice that some of the determinants were 0? Back in lesson 10, wasn't the one on the quiz the determinant was equal to 0? Well, what if I ask you to find the inverse of a matrix whose determinant is 0?
Well, if you know it's undivided.
That would be 1 divided by the determinant, but if the determinant is 0, you can't divide by 0, so the inverse wouldn't exist. Not all 2 by 2 matrices, or not all square matrices have an inverse, only if the determinant is non-zero. So this one, for example, on your quiz, we found the determinant okay, but if I now turned around and asked you to find the inverse of that, what would you say? The inverse doesn't exist. Why does it not exist? The determinant is 0. Okay? Let's do, ooh man. We really don't have time for another example. We got to get on to a 3 by 3.
We should take a nap.
Inverse of a 3 by 3. This is not going to be fun. Well, you remember the determinant of a 2 by 2 is pretty easy, right? But then once we did a 3 by 3, it wasn't quite as enjoyable. It's just kind of the same thing here. For me? Thank you. All right. You ready for this? Instead of doing it with a general matrix, let's do a specific matrix. So we're going to do the matrix. The first column is 1, 2, negative 3. Next column is negative 2, negative 3, 6. Then we have negative 4, negative 6, 15. This is matrix 8. Whew. You got it? I'm going to try to go slow, but we only have 12 minutes. Might not be enough time. So, step 1 is to form the matrix of minors is what it's called. Matrix of minors. I love all the names for these. So a matrix of minors. It's still going to be a 3 by 3, so you're going to have matrix of minors is what it's called. Think back to our last lesson 10.6. A minor is a determinant of part of a 3 by 3 matrix. For example, if I crossed out this row and that column, What's the minor of that? It's not just that matrix, it's the determinant of that matrix. You see what I mean? So that's what's happening here. We have to find every single minor by crossing out every single row and column. Okay, so this first minor right here means you have to cross out this row and that column. Okay, and we have to do that for all of them. So, rather than... me, I created this. This is my idea.
I do that, like, I used to really hate system, what was it? Solving for 3 solutions or whatever. But I really want to go back to that.
Yeah.
So does that, like, I want to
We're going to do that too. So let's go, you guys. Let's take too long. Zip it. Zip it. Zip it. Zip it. Come on. This first one right here. That row, that column's gone. Let's do the math. Shh, shh, shh. So this minor is going to be negative 45 minus negative 36, which is plus 36. All right. Now let's go on. If I want to find this minor, then you have to cross out second row, first column. So what's that minor going to be? It's negative 30 minus negative 24, which is plus 24. Now we move on. I know I'm moving fast, but this is stuff you should be able to do. How do you find the minor that goes here? Well, you cross out the first column and which row? Third row. Now find that minor. That's going to be 12.
12 plus 12.
What is it? We got to be careful with the arithmetic. It's 12 minus 12. Okay, now we move on. I want to find the minor that's in this spot right here. So which column and row do I cross out? First row, second column. Now that minor is going to be 30 minus 18. Now this minor right here is right smack dab in the middle. So that's second column, second row. So it's 15 it's minus 12. Here's what's happening, Nick. What's this cross product here? And what's this cross product? So you minus them. It's AD minus BC. But the reason some of these are turning into plus is because it would be minus a negative. So this one right here, this one right here, bottom row, second column, it's going to be negative 6 times 1, which is negative 6, minus the other cross product. What's this other cross product?
It's negative.
Negative 8, but if you're minusing a negative, it becomes plus 8. Okay, now we move on. This minor right here is top row, third column. That's going to be 12 minus 9. Okay, this one right here is the middle row, third column. 6 minus 6. And finally, last row, last column, we're going to have a negative 3 minus negative 4, which is plus 4. Woo! So let's figure out what we have. That first entry is, help me out here, negative 9. Keep going, negative 6, 0, 12, 3, 2, 3, 0, 1. Okay, we get so, I mean, I know that's not enjoyable, but it's doable, right? Next thing we got to do is follow this pattern here. We've got to change some of these signs. Now, if it's in a plus spot, then the sign is what it is. So this negative 9 is in a plus spot. So what do we do with that negative 9? It stays negative 9. But down below it, this negative 6 is in a negative spot. So what happens to it? It becomes positive 6. 0 doesn't really have a sign, so it just stays 0. What about the 12? It's in a negative spot, so it becomes negative 12. The 3 is okay to stay at 3, but the 2 becomes negative 2. And then in the last column, 3, then what? 0, and then 1. Okay.
So basically, like, you just take the two sides.
Yeah. This is not the inverse yet. This is not the inverse. We're about halfway done. Yeah. That's negative 2 right here, yeah. Now, this is a new concept that we haven't talked about. It's called transposing. Now transpose the matrix. This is step 3, I guess, because step 2 would have been to use this plus minus plus matrix. The transpose of a matrix is the columns become the rows. Okay?
So we just kind of
Columns become rows. So for example, what am I circling right here? Isn't this column 1? Okay, so that becomes row 1. This is column 1, right? So to transpose it, that becomes my row 1. Nope, you keep the signs as they are. So this column right here, where do I put this column?
on the top.
On the top. It becomes negative 9, 6, and 0. Okay? Now this is similar. I know it looks a lot different, but it's somewhat similar to what we did with the 2 by 2. Didn't we have to switch the spots of some of the terms inside of the inverse for a 2 by 2?
Yeah.
That's exactly what we're doing here. We're just switching the spots of some of the terms. And didn't we have to make some of the terms positive and negative? So I know it looks different, but it really does pattern itself off of a 2 by 2 matrix. Now what about this middle row, or this middle column right here? Where does it go?
On the second row.
That becomes the middle row. So it's negative 12, 3, and negative 2. And finally, this last column becomes your bottom row. 3, 0, 1. That's called the transpose of a
There are
matrix.
too many places where you can make mistakes.
Finally, step 3 is to multiply this by 1 over the determinant. That's the last step, 1 over the determinant. Okay, we've got to go all the way back to the original matrix and find the determinant now. So the determinant of A. So there are not any zeros, unfortunately, so we're going to have to just choose a random row or a column to expand on. So I'm going to choose this row and expand across it. So the first cofactor is 1. Now we multiply it by the minor. But we already know the minor when we cross out that row and column. It's right here. What is it? Is it a negative 9?
Yeah.
Now we subtract the next cofactor. What's the next cofactor? 2. And then we multiply it by the minor. But we already know what the minor should be in that spot. Where's the minor from that spot? Negative 6.
Oh, keep going down.
I'm going down the column here. And now we choose the next cofactor, which is negative 3. And then we multiply it by the minor that's in that spot. What was the minor in that spot? 0. So this becomes negative 9 plus 12, which is 3. So the determinant is 3. So we go back here and we take this 1 over 3 times negative 9, negative 12, 3, 6, 3, 0, 0, negative 2, and 1. And now we're ready to find the inverse. If we multiply everything in there by 1/3, we're going to get come on now. Negative 3, negative 4, 1, 2, 1, 0, 0, negative 2/3, and 1/3. Woo!
That wasn't that bad.
We finished in the nick of time. Okay. Here's the thing. Listen. This is important. We are not quite finished with everything that we need to do in 10.5 or with matrices in general. So test is not going to happen on Wednesday. Okay? There's just, I don't want to rush this stuff. We're going to have to do a little bit more Wednesday, then review Wednesday, then test on Friday.